Hey, math peeps. So we're going to take a look at lesson 2 now. And for lesson 2, we're going to concentrate on looking at derivatives of exponential functions, okay? So just like we did with trig, I know I said that on the last lesson too, but we want to kind of develop a couple that you want to recognize, and then we'll use those in more complicated situations, okay? So what we're going to start with is we are going to try and figure out how we would get the derivative of b to the x, okay? And we're going to do it using first principles. So we're going to say that the derivative of f of x will be the limit as h approaches 0 of f of x plus h minus f of x all over h. That is the definition of derivative using first principles, okay? So for f of x plus h, that's going to be b to the x plus h. I'm looking at this equation up here. Okay, this is the one I'm working with. So b to the x plus h minus b to the x all over h. Okay, so now we need to figure out what can I do with this. And the first thing I want you to notice is I want you to take a look at this. This is not something we do often, so it's not always something that comes right to your head. But if this says b to the x plus h, think about your exponent laws for a second. If we were multiplying exponents that had the same base, if we were multiplying powers that have the same base, we would add the exponents together. So if this is an exponent where two things are added together, that means it must have been at one point b to the x times b to the h. B to the x times b to the h would have given me that b to the x plus h. Okay, so I'm going to write b to the x plus h as b to the x times b to the h. Now, why would I want to do that? Because now I have two terms on the top here, and both terms involve a b to the x. So I can factor the b to the x out, okay? When I go to factor the b to the x out, I'm going to have b to the x times b to the h minus 1. And what I want you to notice there is that b to the x actually has nothing to do with the limit anymore because there's no h involved. So I'm also then going to move the b to the x up to the front. It's like it's a coefficient now, so I'm going to move it to the front of my limit, okay? I'll clear that ink there. So the b to the x can be factored out, which we did. And then we're going to move it to the front of the limit because b to the x does not depend on h. Okay, so I'm going to move this guy here up to the front. And then I'm going to be left with the limit, so b to the x times the limit of b to the h minus 1 over h as h approaches 0. So then I need to figure out, well, what the heck is this going to be? Okay, so now we're going to kind of take a sidebar here. We're going to do a little investigation together, and we're just going to look at this and try and figure out, as h approaches 0, what would we end up with here? Okay, now to do that, I've given you a table, and we're going to approach a few things. So we're going to take a look at when b is 2 and when b is 3, just to see if we can figure anything out. Okay, so somehow we need to determine that limit. Complete the following table using your calculator to estimate the limit for b equals 2 and b equals 3. Okay, so we've got you set up in the following table. I've done already when h is 0.1, so now we're going to take a look at when h is 0.01 and then 0.001 and then 0.00001. Okay, so pause me for a sec and fill in those numbers. Don't worry about the ln x yet. I just want you to get the numbers in first. So the first three, or the next 3 rows, is what I want from you. Okay, so this is what you should have gotten. Okay, and so we're approaching, it looks like we're approaching 0.69 for sure. And over for 3, we're approaching 1.0986. Now what I want you to do is I want you to check what ln x is. So remember, we're looking at 2 and we're looking at 3. So in your calculator, figure out what ln 2 is and what ln 3 is. And what you're going to notice is it's actually the same digits as when we got all the way down to 0.00001. Okay. So what are we saying? We're saying when the b value was 2, we end up approaching a limit of ln 2. And when the b value was 3, we ended up approaching a limit of ln 3, okay? So the limit when b was 2, we ended up approaching ln 2. And the limit when b was 3, we ended up approaching ln 3. Okay, so we need to put these two pieces back together to say what the derivative was. Remember what we're trying to do in the first place is we're trying to figure out the derivative of b to the x, right? And when we started this with first principles, we ended up factoring out a b to the x and sticking it to the front. And then this is the second chunk that we're trying to figure out what it means, okay? And now what we see is that second chunk, that b to the h minus 1 all over h, that limit is going to approach ln of b, okay? So the derivative becomes b to the x ln b. So this guy here is the derivative of b to the x, okay? The derivative of b to the x is b to the x times ln b. So the derivative of 2 to the x is 2 to the x times ln 2, and the derivative of 3 to the x would be 3 to the x ln 3. Okay? Okay, so what about e to the x? Well, same conversation. It would be e to the x ln e, right? But I want you to stop for a second. I want you to think about what ln e is. Because remember, ln is log base e. So really, ln e is saying log base e of e. And we know that log base e of e is 1, right? Anytime the base and the thing you're taking the log of is the same, that just gives you 1, right? Log base a of a is 1. Log base b of b is 1. Okay, so ln e is just 1. So the derivative of e to the x is actually just e to the x, because it's e to the x times 1. And that'll give me e to the x. Okay, so things we have figured out so far, if f of x is b to the x, then the derivative is b to the x times ln b. And if f of x is e to the x, then the derivative will just be e to the x. Okay, again, because it's e to the x ln e, but ln e is just 1. Okay, and just in case you're starting to get stressed out, those guys are on your formula sheet. Okay, so that was the basic derivative. Obviously, then we can add a layer of complexity to it. So for more complicated exponential functions, we would have, if we were looking at the derivative of b to the f of x, so now it's not just b to the x, but there's some sort of inside function as the exponent. Well, that's the chain rule kicking in, right? So that's going to be b to the f of x times ln b times the derivative of the inside function, so the derivative of f of x, okay? And same thing with e. The only difference is that ln e actually isn't going to be stated because ln e is just 1. So it becomes e to the f of x times the derivative of f of x. So when you have a function on the inside, you have to take the derivative of the inside function as well, okay? So let's practice a few together and see how we're doing. First guy, y equals e to the 2x. So the derivative of that is going to be e to the 2x times the derivative of the inside function, which is 2. So I'll have 2 e to the 2x. Okay, nice simple one to start us off with. All right, now we're going to take a look at e to the root x plus 1. So the derivative of e to the root x is e to the root x times the derivative of the inside function. Well, that inside function is the root of x, which is x to the 1/2. The derivative of x to the 1/2 is 1/2 x to the negative 1/2. Okay, so I'm going to have 1/2 x to the negative 1/2 times e to the root x. Whoops, I just got to get my mouse back, sorry. Okay, now we're going to clean that up a bit. E to the negative 1/2 is just root x on the bottom of the fraction. So I've got 2 root x on the bottom, and I've got e to the root x on top. So that would be the simplified derivative. Okay. All right, determine the slope of the tangent to the curve y equals e to the sine of 2x when x is pi over 2. Well, the first thing I got to do is take the derivative. The derivative of e to the something is e to the something times the derivative of my something, right? The derivative of the inside function. Now, the inside function is sine 2x. The derivative of sine 2x would be cos 2x times the derivative of that inside function. That inside function is 2x, so the derivative of that is 2. Okay, so we're going to stick all that together, and we get 2 times cos of 2x times e sine of 2x. Okay? Now, that is the derivative. That equation represents the slope at any point along my original function, the slope of the tangent. But I want the slope when x is pi over 2. So now what I'm going to do is I'm going to plug pi over 2 in for x. Okay, so I just took my derivative function and I am plugging in pi over 2. 2 times pi over 2 is pi, so this is going to be cos of pi, and over here it's going to be sine of pi. The cos of pi is -1. The sine of pi is 0. So 2 times -1, e to the 0 would be 1. So I end up with -2 altogether. Okay, so the slope of the tangent will be -2 at x equals pi over 2. Okay. All right, determine y prime. Okay, so there's two different ways you can look at this. We could either look at it as the quotient rule, or I could bring that 1 minus e to the x. I could call that 1 minus e to the x all to the -1 and use the product rule instead. Okay, it doesn't really matter which one you do. I chose to use the product rule for this one. So the first thing I'm going to do is rewrite it as a product. So I've got 2e to the x squared times 1 minus e to the x all to the -1. Okay. Okay, so I'm looking at derivative of f times g plus f times derivative of g. So let's deal with the derivative of f first. 2e to the x squared. Well, that's going to give me 2e to the x squared times the derivative of the inside function. So the derivative of x squared would be 2x. Okay, times g, which is this guy, plus f, which is this guy, times the derivative of g. Now the derivative of g would be -1, this to the -2, times the derivative of the inside function, which would be -e to the x, times the derivative of that inside function. Okay, now that inside function was just x, and the derivative of that was 1. Okay, so just to repeat myself, okay, the derivative of f was 2e to the x squared times the derivative of the inside function. And then that was my g, and then plus f times the derivative of g. So I moved my -1 to the front, times that guy to the -2, times the derivative of the inside function. Okay. Okay, now I want to work on cleaning up a bit. This 2x can get multiplied with that 2, so that'll be 4x in the front. And here I got a -1 and a -1, so that's actually just going to be a +1. So that'll just be 2e to the x squared in the front of that guy. Okay. Now I can factor out some stuff. I can factor out a 2. I can factor out an e to the x squared. And I can factor out a 1 minus e to the x to the -2. Okay, so this guy here is all the things I just said I was factoring out. And then what I'm left with, when I take this first term and divide by 2, I'm left with 2. My x I didn't do anything with. The e to the x squared is gone. And then I have, this was to the -1, so that leaves me with 1 minus e to the x. And then over here, the 2 is gone, the e to the x squared divided out. I'm left with e to the x, and this one I factored out. okay? So now the 1 minus e to the x to the negative 2 can come down to the bottom, and that will be squared. I'm going to multiply this through, okay? And that would leave me with 2e to the x. I sent my 1 minus e to the x squared to the bottom. And then I've got 2x minus 2x e to the x plus e to the x. Okay, there's no other factoring that can happen there. There's nothing common to these three terms inside here. So that is in simplified factored form. Okay. Awesome. All right. Determine the derivative of y. So this is implicit differentiation. I've got y happening with x at the same time. So I'm going to take the derivative of both sides. The derivative of y is y prime. This guy, let me just circle that for you. I need you to see this guy as the product rule. Okay, so we're looking at the derivative of y times g. So that would be e to the x squared plus y times e to the x squared times 2x, the derivative of the inside function, okay? And then there'll be a 2 in front of that. And then the derivative of 4x cubed would be 12x squared. Okay, so that gives me this. Now, I will distribute this 2, and that 2 is also in front of this term. So this is going to be 2y prime e to the x squared plus 4y e to the, or 4x, sorry, y e to the x squared plus 12x squared. Now remember, with implicit differentiation, we want to get all our terms involving y prime onto one side and all the terms not involving y prime to the other side. So I'm going to take that 2 y prime e to the x squared over to the other side, so it'll be minus. Then I can factor out the y prime, so that's going to leave me with y prime in brackets 1 minus 2e to the x squared. And I'll just divide both sides by 1 minus 2e to the x squared to get y prime all by itself. Okay, I also want to take a look at this side here, and I can see I could factor out a 4x, so I want to do that as well. Okay, so I factored out a 4x from the top. That left me with y e to the x squared plus 3x all over 1 minus 2e to the x squared. Okay, cool. All right, so that's it for this guy. I'll leave you to do some practicing. And then in our next lesson, we will tackle derivatives of logarithmic functions. Okay, if you have any questions, you know where to find me. Don't be a stranger. Okay, take care, guys.